All right, so today we're going to look at a topic called improper integrals, and this is section 8.8 in your textbook. Up until now in Calc AB and this year, when we've worked with integrals over a closed interval, we would use the fundamental theorem of calculus to evaluate the area under a curve over a closed interval. Sometimes we want to work with integrals for functions where the function or the limits are infinite or go on forever, and these are called improper integrals. So let's look at a picture. Let me show you what I mean. So let's consider the function y equals 1 over x squared. I gave you this function, I said, evaluate the integral of 1 over x squared from 1 to b. We would find the antiderivative, which is negative 1 over x. And then we would apply the fundamental theorem of calculus, of course, take the value at the upper limit minus the value at the lower limit, and we would get this expression. So what I want you to think about is what's happening as b goes out to infinity. So as this value we stop at, if it keeps going, do you agree that this would become an unbounded region? That's what we asked in the function. Instead, we're going to write this integral as the integral from 1 to infinity of 1 over x squared. Now, since there's not a number here, we're going from 1 to infinity, what we're going to do is we're going to rewrite this as a limit of an integral. So now we're looking at the limit of the integral from b to infinity of the function from 1 to b. So all I've done is I've replaced this upper limit with b, and I'm taking the limit as b goes to infinity. So remember what we had when we did the antiderivative for this? Up here we had negative 1 over b plus 1. So if I said what's the limit as b goes to infinity, think about what happens. This first fraction is going to zero out, and we're just left with 1. So what we'd say here is that the area converges to 1. And what's really going on is as b is getting larger, if you were to keep calculating areas from 1 to that number, say 1 to 5, 1 to 100, 1 to 1,000, 1 to 1,000,000, calculate the areas under the curve, the values you get for those areas would converge or get close to a value of 1. You'd get 0.99, 0.99999, 0.9999999. The values would never actually equal 1, but they would get closer and closer to 1, like a limit. This is called an improper integral. And we have some rules here that we need to remember how we're going to rewrite these functions when we're working with them. So rule number 1, if f is continuous on the interval from a to infinity, then the integral of the function from a to infinity turns into the limit as b approaches infinity from a to b. So this is like the example we had in the last problem. A is a constant. We rewrite it as the limit as b goes to infinity. If f is continuous on the interval from negative infinity up to b, then the integral from negative infinity up to b of that function, we change that lower limit to a and write it as the limit as a goes to negative infinity up to b, where b is a constant. And then the last case is if f is continuous on the interval from negative infinity to infinity, then we break this up into two integrals, and we say the integral from negative infinity to infinity becomes the integral from negative infinity to c, plus the integral from c to infinity. And c can actually be any number on the number line. Usually we choose 0 just to pick a convenient value. And we'll see some examples of these. In those first two cases that we would say that the integral from a to infinity, which is really this limit, or the integral from negative infinity to b, which we really write as this limit, as long as that limit exists, then we would say that the improper integral converges to that number. If for some reason that limit is b and e, either it goes to infinity or it doesn't exist, then we would say the improper integral diverges. In that third case, where we broke it up into two separate integrals, either integral on the right diverges, then we say the integral on the left diverges. Let's look at an example and see how we would actually work one of these problems. Here we have the integral from 1 to infinity of 1 over x dx. First thing I want you to do is rewrite that as the limit as b goes to infinity of the integral from 1 to b. You need to get in the habit of writing those limits. I'm going to be really picky about that. The antiderivative of 1 over x, of course, is the natural log of x. So now I'm looking at the limit as b goes to infinity of the natural log of x from 1 to b. Apply your fundamental theorem of calculus. It turns into the natural log of b minus the natural log of 1, which of course is 0. So then you're just asking yourself, what is the limit as b goes to infinity of the natural log of b? Of course, that's infinity. So we would say, since there is no limit here, it goes to infinity, we would say that the improper integral diverges. So what's going on with the area is that if we kept integrating and looking at areas under this curve from 1 to really, really big numbers, the numbers will just keep getting bigger and bigger and bigger. They're never going to approach or converge to a number. Okay, let's look at another example. So this time we have the integral from 1 to infinity of the function 1 minus x times e to the negative x dx. So since we're taking this from 1 to infinity, let's go ahead and rewrite this as the limit as b approaches infinity of the integral from 1 to b. Then we're going to integrate this. Now this is going to require integration by parts. So I went ahead and made u the polynomial 1 minus x and the dv the e to the negative x dx. The derivative on the left side is negative 1. The integral on the right side is negative e to the negative x. So we have negative e to the negative x times 1 minus x. There's your uv minus the integral of b du. And then that can just be integrated. This. So when we clean it up, notice those first and last terms cancel, and we're down to this. Now remember your fundamental theorem. We're integrating this from 1 to b. So if we apply the fundamental theorem, this turns into b over e to the b minus 1 over e. Make sure you've seen what I've done here. I just moved the e terms to the denominator because they have a negative exponent. And then remember, we were taking the limit as b goes to infinity. Now, if you want to, you can use L'Hopital's rule. The limit of b over e to b as b goes to infinity, that would be infinity over infinity, so that turns into 1 over e to the b when we apply L'Hopital's rule, which just takes us to 0. What does that leave us with for the integral? Negative 1 over e. So we would say that this integral converges, and the area under the curve converges to the value negative 1 over e. And notice it's negative. Here's a picture of the graph. The only reason it's negative is because it happens to all be under the x-axis, but the area would be 1 over e. All right, last little example here. So this is at case 3. We have the integral from negative infinity to infinity of e to the x over 1 plus e to the 2x. Whenever you have the integral from negative infinity to infinity, you're going to break it up somewhere on your number line and choose whatever c value you want. It really doesn't matter, but I think c equals 0 is the easiest number to split it up. So here's what I mean. We're going to write this as the integral from negative infinity to 0 plus the integral from 0 to infinity. Just make sure you see that that just covers your entire number line. Now, both of these, if we did a little u substitution and let u equal e to the x, we would have 1 over u squared, which is arctan. So this becomes the integral of arctan e to the x. Now, notice how I rewrote this first integral. Now, I used b here. Earlier in the PowerPoint, I used a. It doesn't really matter what variable you're working with. I just use b kind of as a matter of convention, but make sure you see what I did. I just changed this lower limit to some variable. I called it b, and I'm going to take that limit as b goes to negative infinity. And then the other one I wrote as the integral from 0 to b. I'm going to take the limit as b goes to positive infinity this time. Okay, you really need to think here about what the graph of arctangent e to the x looks like, or at least the arctangent graph. If we use the fundamental theorem of calculus, we've got arctan of e to the 0, of course e to the 0 is 1, so this first term is just pi over 4, minus arctan of e to the b. And over here we have arctan of e to the b minus arctan of e to the 0 again, which is pi over 4. Okay, so you probably haven't seen an arctan graph in quite a while, but let me just give you a little refresher here. So this is the graph of the arctan e to the x function. Remember, this is what we're looking to evaluate. So think about as b approaches negative infinity. Now, even if you don't remember what the graph looked like, if this exponent is going in the negative infinity direction, that's going to be like 1 over e to the b, and all of those numbers are going to get larger on the denominator and force this 1 over to go to 0. And arctan of 0 is just, of course, 0. And you can see that from the graph as x, or b rather, goes out to negative infinity, this arctan graph is going to approach 0. Now on the other side, what's going on? Remember the arctan graph actually has a horizontal asymptote at y equals pi over 2. So as b goes to positive infinity, in this direction, this is actually approaching pi over 2. So what we're looking at now is pi over 4 minus 0 for the first limit, plus pi over 2 minus pi over 4 for the second limit, or just pi over 2. So that's the first half of improper integrals, and we'll look at the next half tomorrow.